Okay, so some people are here, so let us start now. Let me share my screen. So Unit 5 is about field theory, okay, and for some parts I will use these notes. Okay, so this is a course, an old, very old course from Infotech. Okay, it is not active currently. It's old course, but there are notes here. I'll post the link in MS Teams little while later. Here there will be some printed notes and PDF and all those things. So for example, here if you go to, if you just open this link, this thing opens, right? And here you have these slides. So here you go on clicking next, 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 and you have lots of slides. And okay, you go to downloads, there's a full collection of lecture notes, and there will be lots of PDFs. We don't have to do everything. This is a very big course. We don't have to do everything that is done in this. Okay, so if you see there are some 25 lectures or 26 lectures in this course, we don't have to do all of these. We have to do probably about 7 or 8 lectures only, maximum, not nothing more than that. Not even 7 or 8, I think, about 7 or 8. Okay. And then some other stuff from other parts I will share with you. But yeah, so this is a good place, and I will give you sections to read from these notes after we complete each lecture. Okay, so that is there. That what else should I say? Okay, so another good resource is let me check if I have it. Okay, so do you people know book by Gallian on algebra? Contemporary abstract algebra by Gallian. Have you heard of Gallian's book?
Yes, sir.
So
Yes,
Gallian,
sir.
गैलियन में भी फील्ड थियरी का एक सेक्शन है, वहां से भी थोड़ा सा पार्ट कवर करेंगे। तो गैलियन का पीडीएफ मैं फिलहाल नहीं है, ढूंढ के मैं पोस्ट कर दूंगा एमएस टीम्स में, and then we'll refer from that. So I don't know, I may not be able to write down too much in slides, वगैरह, but I'll take you through these notes or sections from the book and so on. Okay, so that is how we do the, that is how we proceed with the course. ठीक है, तो शुरू करते हैं, थोड़ा सा करते हैं आज, maybe 10-15 minutes, and so introduction and overview is not a big thing. You can read this part. It is just very basic introduction about history of field theory and etc. etc. We are not. It's not important as far as your exam is concerned. But yeah, take your time and read through these slides whenever you get time. It is just for motivation. Okay. So okay. So all of you are familiar with field cut definition.
Yes, sir.
So okay, then good. So let us just recap. Yeah, from Wikipedia. Okay, that's a good place to. Okay. So of course, intuitively, field is a set on which addition, subtraction, multiplication, division can be defined and behave nicely, etc., etc. Okay. The definition that we are interested in is this, right? It's a set with two binary operations, addition and multiplication. Okay. Or but you have already seen some of these axioms already: associativity, commutativity, additive identity, additive inverse, distributivity of multiplication or addition. You have seen all these things in definition of a ring, right? Ring theory चल रहा है ना आपका. So commutative ring with unity covers most of these axioms except multiplicative inverse, right? In a general commutative ring with unity, multiplicative inverse need not exist. For example, you can take Z mod 4Z and then you can find out elements for which inverses don't exist. Right? Can you give an example of Z mod, an element in Z mod 4Z for which multiplicative inverse is not there? Z mod 4Z मैं जब कह रहा हूँ आपको समझ में आ रहा है ना what I mean?
Yes, sir.
Yeah. Give me one element in Z mod 4Z which does not have a multiplicative inverse. One non-zero element. One non-zero element that is not invertible in Z mod 4Z.
Sir, 2 का inverse नहीं है ना?
Correct. Because you just multiply 2 with every element. 2 into 0 is 0, 2 into 1 is 2, 2 into 2 is 4, but mod 4 is 0. 2 into 3 is 6, which is mod 4 equal to 2. So 2 into any A is not equal to 1. Therefore, 2 has no multiplicative inverse, right? So in general, it's not true. But whenever a commutative ring with unity says that all non-zero elements, uh, whenever a commutative ring with unity is such that all non-zero elements have an inverse. Okay, there is an inverse which we denote by A inverse or 1 by A, such that A dot A inverse equal to 1, A inverse dot A is also equal to 1. That comes from commutativity. Right? Then we call it a field. Okay, all non-zero elements are invertible. That is a definition of a field. Commutative ring with unity, where all non-zero elements are invertible. So now, can you give me an example of a field? Have you seen a field anytime? These are simple questions, so I want answers quickly. Have you seen a field?
X number का rational.
Set of all rational numbers is a field. Okay. What else? Anything else?
Real.
Set of all real numbers is a field. Okay. Then
Z with modulo P prime.
very nice. Z mod PZ, where P is a prime, is a field. Correct. Set of all complex numbers is also a field. अब real पे बोल के रुक क्यों गए? Rationals, reals, complex numbers is also a field. Right? What about set of all integers? Is it a field?
It's not a field.
Why?
सर इसमें इनवर्स नहीं होता है ना?
हाँ तो प्रूफ अगर लिखना है तो क्या कैसे प्रूव करेंगे? Z is not a field.
कॉन्ट्रडिक्शन से कर पाएंगे, लाइक अगर फील्ड है तो उसके डेफिनेशन वाइज जाएंगे, बट हमें इनवर्स तो मिलेगा नहीं, तो फिर
आप एक if you just have to say that I give you a statement Z is a field, true or false with justification. ठीक है, अगर false बताना है तो आप क्या करेंगे? अगर false बताना है तो आप काउंटर एग्जांपल दें. कोई एक काउंटर एग्जांपल दे सकते हैं Z में? What do you mean? What do you have to show? What counter example do you have to give to say that Z is not a field?
सर सपोज हमने 2 ले लिया तो उसका कुछ मल्टीप्लिकेटिव इनवर्स Z में है नहीं.
हाँ तो वही. So counter example is there exists an element in Z such that there is no multiplicative inverse. Okay. तो 2 का multiplicative inverse नहीं है. क्यों?
क्योंकि 2 इंटू सपोज m लिया इक्वल टू आइडेंटिटी होना चाहिए, बट फिर m का वैल्यू रैशनल आ जाएगा और रैशनल तो इंटीजर में आता नहीं है, तो नहीं है.
आप प्रूफ हिंदी में लिखने वाले हैं क्या एग्जाम में अगर मैं पूछा तो?
9.
So just tell me the answer now. Suppose you are writing it down on a piece of paper. What is the proof? What is the answer? आप एग्जाम में कैसे लिखेंगे?
2 into m is equal to 1. M is equal to 1 by 2, which does not belong to set of integers.
Okay,
So we cannot find an.
fine. Take it. So 1 by 2 is not an integer, and therefore inverse doesn't exist in Z. Okay, fine. So examples are rational numbers, just as you said, real and complex numbers, just as you said, something called constructible numbers. Okay, so we will learn constructible numbers in this course. In this unit, we will come across constructible numbers, but currently, just remember that this is an example. Okay, we will need this. So basically, constructible numbers are all those numbers which can be obtained as some side length obtained via some geometric construction. Side length of a triangle, rectangle, or some such figure, or radius of some such circle that you get at the end by drawing some suitable construction. Once you do that, whatever numbers you get, those are constructible numbers, and that will form a field. In fact, that will be a subfield of all, that will be a subfield of real numbers. Okay. So for example, before we go with details, one very nice example of a constructible number is square root of 2. Okay, forget this part. Don't read what is written. I'm just saying square root of 2 is a constructible number because you can take a right angle triangle with side, base and height equal to 1. What will be the length of the hypotenuse?
Root 2.
So that is the meaning of construction. You can draw a right angle triangle, right? You can construct a right angle triangle with base and height equal to 1. Just draw a line segment of length 1, then take a perpendicular to that line segment, and then again mark a line segment of length 1. Then join the 2 points. So you have the hypotenuse, right? So you have constructed a triangle. One of whose sides, that is the hypotenuse, has length square root 2. So square root 2 came from a construction. So square root 2 is a constructible number. Okay, that is the basic idea. Okay, so constructible numbers will form a subfield of real numbers. So we will go to finite fields. So this is fine. This is fine. Characteristic पता है आपको? Ring का characteristic तो आपने देखा होगा.
Yes, sir.
Right? So can you say what will be the characteristic of any field? Okay, so we will see in the next lecture, this will be the first thing that we prove, that the characteristic of any field can either be 0 or a prime number, nothing else. Okay, the characteristic of a field cannot be 6. The 6 is not a prime number. Okay, so it is like this. Basically, you have Z mod PZ where P is a prime, it is a field, right? So P is prime. So characteristic of Z mod PZ will be P. When characteristic is 0, you have fields such as rational numbers, real numbers, and so on. And up to characteristic, these are the only kinds of fields that you can have. Okay, there are larger fields that you can have, but there will be some smaller subfields of this kind all the time. So characteristic will always be P or 0. We will prove that in the next lecture. But other than that, it's not possible. So there is no field with characteristic 10. Do you understand? There is a ring with characteristic 10. Can you name one ring with characteristic 10? A commutative ring with identity with characteristic 10. सामने एग्जाम्पल है. स्क्रीन पे मैं जो शेयर स्क्रीन कर रहा हूँ सामने एग्जाम्पल है. Commutative ring with unity with characteristic 10. सामने एग्जाम्पल है. Do you remember characteristic of a ring? यूनिट 4 में चल रहा था ना, यूनिट 3 या यूनिट 4 में कैरेक्टरिस्टिक किया होगा ना.
Yes, sir.
हाँ, so what is an example of a ring with characteristic 10? मैं बार बार बोल रहा हूँ सामने एग्जाम्पल है, मैं कर्सर से हाईलाइट कर रहा हूँ, फिर भी अभी तो बताओ.
Z mod 10Z.
Okay, Z mod 10Z has characteristic 10. In general, Z mod NZ will have characteristic n. Okay.
N.
So do you see what we just said also works for all Z mod NZ? Z mod NZ has characteristic n. But a field can have characteristic only 0 or p, a prime p. So Z mod NZ can be a field only n is basically 0 or a prime p. So it is Z mod PZ or Z mod 0Z, which is Z itself. Okay, but Z itself is again not a field. Okay, so it is not if and only when you consider Z mod NZ. But if P is not a prime, definitely Z mod NZ cannot be a field. Okay. So these were simple examples. History, vagara, not very interested. Constructing fields, we will look at it a little bit. Field extensions are the main thing that we want to study. Okay, so I'll give you some things to read. Not from Wikipedia. Wikipedia is usually too detailed. Okay. Galois theory बोल के एक field होता है, but we will not get into Galois theory. If you want to learn later, maybe you will have a course. I don't know, but yeah. So that is it. Okay, so let me just begin a little bit from lecture 2 in this link. Okay. Lecture 1 is not important. You can read it for some introduction if you want. Okay. The same thing is available in the lecture notes when you click it. Okay, download and read. It is already there. Or I'll share it in MS Teams. I'll share these PDFs with you. So let's look at this. Okay. So we are going to learn what is called an algebraic extension. Okay. So before that, some basics. We look at main examples of fields to be studied. What is the meaning of minimal polynomial of an algebraic element? What is the meaning of simple field extensions and what is the meaning of their degree? Okay. Right. So we already looked at some examples. There are also other examples. Okay. So something called a number field. Number field is just a definition. Okay. So a number field is any subfield of C. So do you understand what subfield is? A subring, which is also a field, is a subfield. Okay, that much is clear.
Yes, sir.
So any field that is a subfield of C, subfield of complex numbers, is called a number field. So rational numbers Q is a number field. Real numbers R is a number field. Okay. Any other subfield that you can think of, which is a number field?
Z.
नंबर फील्ड. पिछले 15 मिनट से कह रहे हैं कि Z फील्ड नहीं है. Number field. Okay, so I'll give you some examples. So for example, the set of all pth roots of unity is a number field. It will form a field. Okay. You check that. I'll give it to you as an exercise. Okay. Note that when you want to prove that something is a field, it is usually a commutative ring with unity. You don't have to check all the ring axioms. You only have to check whether the non-zero element has an inverse or not. Okay. Finite fields is something we look at. Function fields are not very important. Characteristic is what we just saw. Okay. So let R be a commutative ring with unity or identity E. This is the multiplicative identity. So this is basically the proof. We'll go through this once again in next lecture, but let me just take you through this shortly or quickly. Consider the ring homomorphism from Z to R. Okay, F from Z to R. How do you define it? F of any integer n is just n times E, where E is the multiplicative identity of R. Okay. What is the kernel? Kernel is set of all n such that ne is equal to 0. Okay, but kernel is a subring of Z. It's an ideal of Z. Okay. Do you remember the kernel of every ring homomorphism is an ideal?
Yes.
So over integers, every ideal can be generated by just a single element. Right? That is something you should have proved. You take more than one elements, but you can still look at GCD and LCM and get a single element as a generator of that ideal. Okay. So every ideal is generated by a single element over Z. So kernel F is an ideal of Z, it is generated by some single integer n. If n is equal to 0, then the kernel is a 0 kernel. So Z is isomorphic to a subring of R. Right? Because this goes into kernel is 0 means F is an injective function. So Z injects into R. So it's a isomorphic to a subring of R. Then we say R has characteristic 0. Okay. Further, if yes, yeah. Further, if it is not 0, then Z mod n is a domain and it is subring isomorphic to a subring of R, and in this case it has to be a prime. Okay, so we'll argue in more detail. Here it is not written in enough detail. We'll argue in more detail that characteristic has to be 0 or P. For example, when the characteristic is not 0, why should this be a domain? Right? These things are not clear. So we'll argue in more detail in the next lecture. Okay. But just remember, characteristic of a field is either 0 or a prime. Okay. I just want to mention a few definitions before we finish. Okay. So let K be a subfield of F. F is a field, K is a subfield. Okay, subring of F, which is also a field. Then F is called an extension field of K. K is called a base field of F. You understand? K is a subfield of F. F is the larger field, K is the smaller field, K lies below F. So F is said to be extension, K is said to be base. And we will write this as F slash K. This means F and K are fields and K is a subfield of F. Right? Now we say an element
Yes.
in F. An element in F, F is an extension field. An element A in F is algebraic over the smaller field K. If there is a non-zero polynomial over the smaller field K, univariate polynomial non-zero over the smaller field K, such that F of A is equal to 0. The element is from the larger field, the polynomial is from the smaller field. That is the main thing here. Element from the larger field is algebraic over the smaller field if there is a polynomial over the smaller field such that the polynomial is 0 at that point, at that element. And if every element of F is algebraic over K, then we say F is an algebraic extension of K. If this is true for every element of F. Okay. If there is an element that is not algebraic, then we say it is a transcendental element. Note that both the pair is important. Okay, you need to know what is the larger field, you need to know what is the smaller field. An element on the larger field is either algebraic or transcendental over the smaller field. So you should be always aware of what is the larger field and what is the smaller field. Okay. Right. So before we go to the next lecture, so this is the end of today's lecture. Next lecture, we'll start with more details, but just look at these definitions. Take the smaller field to be rational numbers. Take the larger field to be real numbers or complex numbers. Okay. K is rational numbers, larger field is real numbers or complex numbers, and find out some examples of algebraic elements. Some examples of real numbers and some examples of complex numbers which are algebraic over rationals. Is that clear? That is your homework before we meet tomorrow. Tomorrow I told you, right? Nitin sir or Gajanan sir ka ho gaya na, so we will do a few details.
Yes.
But this is your homework. Okay. Find out some examples of real numbers and complex numbers which are algebraic over rational numbers. Just look at examples that you already know and check if they are algebraic or not by this definition. Okay, so I will stop here. Now let us meet tomorrow at the lecture time.
सर
हाँ,
सर मतलब ये वाला जो यूनिट हम ऐसे ही पढ़ने वाले हैं मतलब पीपीटी से
पीपीटी है, मैं स्लाइड डालूंगा यहाँ पे जो डाउनलोड है ना, यहाँ पे लेक्चर, ये जो आपको स्लाइड दिख रहा है इनका पीडीएफ है, ठीक है? तो पीडीएफ में MS Teams में अपलोड कर दूंगा, तो आपको बार बार यहाँ पे जाने की जरूरत नहीं।
ओके सर।
और कभी कभी जब मुझे बोर्ड का जरूरत पड़े मैं बोर्ड लूंगा, बट आई विल नॉट राइट एवरीथिंग इन द बोर्ड. फॉर एग्जाम्पल दिस डेफिनेशन इज हियर वेरी नीटली, तो आई डोंट हैव टू राइट दिस इन द बोर्ड. ये पीडीएफ में भी होगा ये डेफिनेशन, तो बार बार बोर्ड में लिखने की जरूरत है. वी विल जस्ट वेस्ट अ लॉट ऑफ टाइम. Okay. Yeah, so I will post this link to this website as well as some of the PDFs in MS Teams. आज वो कुछ देखना नहीं है, आज बस जो PDF में डालूंगा उसमें से algebraic का definition एक बार देख लो. Find examples of real numbers and complex numbers which are algebraic over rationals. That is your homework. Okay, so let us stop here. Tomorrow we'll meet in the appropriate lecture. You know which lecture. So we'll do this.
थैंक यू सर.
Thank you, sir.